Oh, that's a nice touch.
Yeah, now I can read it without glasses. It's so clear. And you could have a second screen with the
Was this home to that, or is it independent?
I can have split screen so I can take notes.
Okay. Oh, it's just,
Get lost in.
Just IETF.
Okay.
Yeah, I sent it. And it's found actually in my history problem because you sent us here.
Thanks.
Okay.
No. You're trying to get something. It's so close. So we figured out. Yep. Is it? Okay.
Good afternoon. Sorry, that was Welcome to Berlin.
We're about to start first idea at the Rtgwg meeting. Please get familiar with not well if you haven't before. IPR rules, we will call IPR. When we go into working group adoption, we'll call IPR.
before last call. As long as we haven't received all the participants responding to IPR, document will not progress. So we've got a document stuck now because people aren't responding. Please don't be on this list. So thanks to AC and Ignis for taking notes. We are still looking for Jabber. Anyone? Thank you, Drew. Please sign the blue sheets. Yeah. So agenda for today is we'll update you what's going on in working group, status of documents, such. We'll have not Pierre Francois but Ahmed Bashandi give an update on SR, TLFA, and microloop prevention, segment routing. We'll have a presentation on segment routing MRTs. So how can MRTs be instantiated with help of segment routing? So the Google speaker is Sam Aldrin, thanks. He'll be talking about gRPC use cases. So description of gRPC as a protocol, probably will postpone it to the next IETF, I assume. And then we'll have Jen to talk about multi-homing in IPv6 scenarios. So just a reminder, so our chapter had been updated a few IETFs ago. We're not only covering faster route and such, we also functioning as dispatch group, so work which doesn't pass in any other working group could be presented here and then potentially could be redirected to some other working group, or not. So 3 new OFCs, 78, 11, 12, and 16. Great work, thank you. We have requested publication for Rtgwg, also known as BGP in large-scale data center. Pending Shepherd review for BGP peak, Rob. Coming, right? We've got new working group drafts. The logical network element and network instance model. The document before is still pending. So the device model is still pending IPR. Please do respond. It's been in the state for over a month. We are in process of being adopted. The multi-home prefixes LFA, please look at it. It's another week. And that's it. Ahmed?
Actually, one second. You can go ahead and get ready, but there is a BOF later on for interledger, and that has some interesting routing aspects, and so we want to do a little advertisement for that. So go ahead and make an advertisement.
Yeah, so we have a BOF on Thursday afternoon. If anyone's interested, it's basically a way to do what the internet is doing for information, but for payment. So payment is nothing else but a message. So you can route it through very much the same principles as we're discussing here. However, there are some subtle differences. It's a very virgin area. We don't have a lot of people with experience with routing, so would very much appreciate your input if you have some time to spare on Thursday and visit our BOF. Thank you very much.
Thank you.
Yeah, good afternoon, everyone. I'm Ahmed Bashandi. Due to unforeseen circumstances, Pierre was not able to come. So I'll talk today about 2 things, TI LFA and microloop avoidance. I hope this thing works, okay. So fast reroute, it has been discussed for years and years, and the objective is to be able to converge, or actually not converge, reroute or re-forward traffic over an alternative path when a local failure occurs. And we want to have a time limit over this rerouting, and we want to make sure that such rerouting or re-forwarding would not cause the packet to bounce back to the rerouting node or bounce back later. So what are we offering today that is not around? So fast reroute local protection has been around. What we offer? Topology independence. You give me a topology that has redundancy, and I will give you a backup path that will not bounce back to you and will not bounce back to anybody along the path all the way to the destination. What else do we give you? We deliver the segment routing architecture. We actually use the segment routing architecture to make sure that we actually kind of steer the packet all the way, or not exactly all the way, until it reaches a safe point where if it flows naturally, it will not basically loop. Segment routing is capable of forcing the packet over any path. I can make it like turn around a little bit and then go this way and come back and then eventually end, but we certainly don't want to do that. What we want to do is to send the packet over the post-convergence path. So we have seen this. I mean, LFA, as I said, has been discussed for a while. If I take any topology, some implementation will say I will prefer one of my neighbors if it's an LFA. Some other topology will say if I cannot find one of my neighbors, I'll use remote LFA. What we want to enforce is send the packet over the post-convergence path. In addition to being topology independent, in other words, it doesn't matter what that post-convergence path is, I will find it and I will force the packet over that post-convergence path. So why is it good to have a post-convergence path? First of all, usually it is within the capacity planning. When we plan the network, we know if this link fails, this is my post-convergence path, hence I will provision the links on the post-convergence path so that it takes care of the link that has failed. Second, it is easy to predict. We know where it is going. I know that when this link path, the traffic that used to go over this link will follow that link, that link, that link, because it is going to these three destinations. Why? Because the post-convergence path after the failure of this link, for this destination is this way, for that destination is this way, for that destination is that way. Segment routing, there is no need for any targeted LDP session, no need for signaling, I don't need to do anything. There is no need to favor one LFA over the other, or I say I would like LFA versus remote LFA. We don't need to do that. And by doing all of this, by actually doing it post-convergence, we actually give the providers or the network operators what they really had in mind. This RFC is out, and if you look at it, it's a nice RFC. It gives the experience. What you get sometimes, you want this, but you end up getting that. You want that, but you end up getting this. I do not want to use an egress PE to be used as a backup path for a core link failure. So we end up having a lot of knobs that the operator has to manipulate to make sure that the LFA that is being selected is something that would not cause more harm than good, or at least is the best one possible. Other than being like a pain to maintain, you really have to go and change this policy whenever you change the topology. So how to do TI-LFA? Basically, I will be enforcing loop-free conversions or loop-freeness over the post-convergence path. Now, everybody knows about the P and the Q space. So Q space is a space where that can reach the destination or a given destination without using the protected element, whether that protected element is a link or a node or a group of links or a group of nodes. A safe place to release the packet and let it flow naturally is in a node that belongs to the Q space. Now, how do we reach that good release point or safe release point? We need to make sure that I will force the packet into the dangerous space. Okay, so there is the P space. I assume that people are aware of this. P space is the set of nodes that the rerouting node or the PLR is able to reach without using the failed element. That's a safe place. If I send the packet because the failed element is over there, I am using this failed element to reach that P node, hence I can send the packet over there. Now, until when I leave the P space and I enter into some other space that is not a Q space, I am not safe anymore. Okay, so I need to get to that queue space. How many segments are there? So link protection, if you have symmetric topology, it's provable that at most 2 segments. In all simulations that we did, 1 is more than enough. Of course, if there is a post-convergence LFA, if one of my neighbors is an LFA, and there's going to be the post-convergence next hop, of course, I'll use it. For the asymmetric topology, in most cases, it is 2 segment was max. There will be few cases that will need more than this. For node protection and local SRLG, never more than 4, rarely more than 2. So if you see that the number 2 is usually a good number that will give you a huge amount of coverage. In the next revision, hopefully we'll have time for that, we will give details about all these results. Another aspect of segment routing is protecting adjacency sets. And this was this, I'll discuss two aspects of it. So let's say I have this sequence. I need to get to AD followed by DF. Now, in that case, if the link AD, the red link, fails, I must send a packet to D, because D is the only one that will be able to interpret DF. In that case, I will send the packet over an alternative path to the far end of the third link. There was another discussion that happened in MPLS, which is suppose that I know, and again, the mechanism by which we know that is really beyond the scope of this document, that the topmost segment or the topmost label is supposed to tell A, please pop this label, it's an adjacency set, and send it to D. And then when we arrive to D, please send it over the shortest path all the way to F. So in that case, well, I say, okay, why do I need to send a packet to D and then from D to F? I can send it all the way to F. Now, how do we do that? Again, this wasn't discussed in MPLS, which I participated in, if I may use the term. So in summary, for segment routing, we are able to protect nodes, adjacency segments. We are able to protect prefixes. We do not need target LDP session. We do not need any signaling in the core. It's full coverage, and statistics actually in simulation show that more than 2 segments is rarely needed. Of course, somebody can cook up a topology, and it's very easy to do that, especially for node protection, where I can enforce, basically, if you have n links, I can force you to use n-1 segments, but then nobody uses such topology.
Ahmed?
Yes.
Francois, for significant amount of time, so if you feel going in depth would be better to provide more clarity, please do so. You've got all the time.
Yeah, I don't have diagrams. I hope I had we had some diagrams on that. But anyway, in the summary of what we said is that we can provide full coverage. We don't need any signaling, and most importantly, we will use post-convergence path if your hardware supports that. Go ahead.
So I've never really understood this post-convergence path thing. You will be post-convergent. You can be post-convergent congruent from the PLR.
Yes.
But actually, you need to worry about it from the point of packet entry in the network. And so I've not really ever understood how you dealt with that component of the solution.
I don't get the statement, so say that again.
Stuart, please introduce yourself.
Sorry? Sure, Stuart Bryan, yeah. So you can deal with it accurately from the point of local repair to the other side of the point of local repair or to the target. But the convergence that you need to worry about, the post-convergence, is actually from the point of entry into the network. And that doesn't even have to go remotely near this point that you're comparing. So I don't understand.
I don't understand what you're saying.
Addressing fast reroute as opposed to micro loops.
Yeah, micro loops is a different story. I'm going to discuss it after this.
Okay.
Okay, this is not micro loop. This is TI. This is LFA. Link failed, node failed, or a group of links fails. I need to send a packet over the post-convergence after the failure of this node link.
So again, I don't understand why you're worrying about the post-convergence alignment. You actually worry about the traffic engineering alignment, but I don't think it really matters where the packets are going to go post-convergence, because they could be going anywhere.
So I need to send the packet, let's say, to Stefano over there. The post-convergence after the failure of Peter is this way, then I'd better send it this way.
Sorry, Rtgwg. You do care about the post-convergent path from the PLR, because the PLR to the destination is probably what you've capacity planned for that, not necessarily the ingress point to the edge point, right? So what is the point is not that we're trying to get right back onto the TE path, if you're using node segments anyway. It's to get back onto the path that's likely to have the most capacity to get there.
Right, but post-convergence, that's going to be the path from ingress to getting there. The packet may not go anywhere near that point post-convergence.
It's post-convergence from the PLR. You're right in that way.
Yes.
But sorry, I was trying to explain why post-convergence from the PLR is actually useful.
Well, on the assumption that the packets will always go to the PLR afterwards. Otherwise, the capacity will be somewhere else in the network to cope with that failure.
Agreed.
So could you also go back to the point where you said 4 were needed?
This
That
one.
there, never more than 4. Is that an observation from the data you've looked at, or is that a mathematically provable statement?
For node and local protection, you can prove that.
Yeah, you've got never more than 4. Is that mathematically provable?
Yes.
Or an observation? Okay, that's interesting.
Yeah, this is again node and local SRG. Remote SRG where a link fails here, link fails there, that's a different story.
Right, but I think you were saying actually that in the topologies you've looked at, Chris Bowers with Juniper, in the topologies you looked at, you can concoct a topology, you haven't seen more than 4, but you can concoct a topology that looks like a wagon wheel, for example, that requires more than 4.
So maybe I should correct this. This is in case of symmetric links. So if you have a node, if you have symmetric links and a node fails, or a group of nodes a group of links attached to the same node fail, then you are limited to 4 segments.
So the one we used in the early days of fast reroute was the wagon wheel, where the costs into the wagon wheel were 1, and the costs around the edge were 10, or some other large number, and the node in the middle failed. And for an arbitrary number of spokes, I'm not convinced that 4 is the number you need.
So let me remember. So yeah, I'm not sure.
I mean, it may be statistically in the models you've looked at.
Yeah, it's probably
but my
statistically.
question,
I tend to agree with you. This one I proved myself. This one is easy. This one
for a link, I could well.
No, I have the proof. The proof is a couple lines. I have the proof myself. I proved it myself. This one I don't remember whether we proved it or not. But basically, I'm using the cartwheel with a number of spokes. This is what I use usually for.
Well, a cartwheel can have an infinite number of spokes.
Yeah, you're right. You're right. So that's what I'm saying. I can cook up a topology where I can give you n-1 links by basically
Yes. In the pathological case, it takes n-1,
which is the cartwheel.
Yes.
Yes. So any other question?
I did just have a question about local SRLG. And maybe if you go to a diagram, one of your diagrams.
Local SRLG means group of links that belong to the same SRLG and they are attached to the same node. So SRLG can be a link here and a link there.
So it's the PLR. The PLR, they're both local to the PLR.
Yes.
So it says, okay, I want to avoid the first hop, better not be in the same SRLG as my failed link. Okay.
Yeah, an example can be a VLAN, for example. I have 1,000 VLANs, they all go over the same physical link.
So there are some implementations which by default would use SRLGs on different line cards, different interfaces and such.
Yeah. Basically, a node protection is a special case of local SRLG. You can think that I am protecting a node by assuming that all its links belong to the same SRLG, if you can think of it this way, which is basically, let's say my next hop, if this next hop disappeared, this is equivalent to all links that are attached to this next hop have disappeared, or all links belonging to this next hop belong to the same
Hang on,
SRLG.
local SRLG is more than just the node, isn't it? I mean, local SRLGs, whatever patch panel the coffee cup got spilt on.
Local SRLGs are, when we say refer to local SRLGs, I mean SRLGs belonging to that node. If you're talking about general SRLGs, yes, you're right. It could be anything.
Right, so it's kind of misleading. I think if you say node protection, everyone knows what you mean by node protection. SRLG affects things may affect things other than the node, including 2 nodes separated in the network.
So that's why I'm highlighting this thing here, local. I'm not sure.
Well, I'm not sure
so
that's
the
a
same node
meaningful
attached. We can rewrite this saying SRLGs attached to a single node. But again, node protection is a special case of local SRLG. Whereas summary, so that is what we have, and implementations are actually available. Any questions? Any other question?
Request from my side, at least for implementation, I'm aware for, would be great to see some text in the draft talking about implementations, who did, and maybe interoperability.
Okay. Well, there is no interoperability here because this is local behavior. That's actually one of the advantages of this behavior. You can plug this behavior anyone in the network incrementally on some line cards, on part of line cards, on all line cards, some interfaces. This is what's nice about it. So there is really no interoperability.
Well, there's interoperability at the SR level that you need to prove.
Like saying that when I insert it doesn't cause any problems, I don't get this.
If it's local, you can do the whole thing locally, right? No other node in the network needs to know you're doing this repair, but I don't think that applies to this, does it? You rely on cooperation from some other nodes to steer the packet where you want it steered.
No.
Otherwise, it's just standard LFA.
No. No.
Really?
Yeah. No, you don't. Maybe.
I confirm, you don't. It's a local.
Stefano, ready?
Stefano Previdi. No, it's pure 100% local.
So Stuart, to the extent that remote LFA relies on, say, LDP functioning properly, this relies on standard segment routing functioning properly, adjacency SIDs and node SIDs.
Yeah. Yeah. Any other question? Okay, micro loop avoidance. Again, it's a classical problem. Something changes, whether it's a link up, link down, node up, node down. We want to make sure that if something happens in the network, if I start sending or if a node starts using the new path, another node that is a little bit slow would not send the packet back to me. We are going to use segment routing again to avoid having to do any signaling and to make sure that the behavior is local. Again, we need segment routing to be functional, just like as Chris mentioned, we need target LDP or RSVP to be functional. The main difference between TI-LFA is that the topology change is not attached to the, I would call it the rerouting node rather than that PLR, because there is no repair. I mean, in theory, it could be a link up. So there is no repair here. We use the term rerouting node or RN. That topology change is not local. It may or may not be attached to the element that came up or went down. Loop avoidance happens during the reconversions following a state change to make sure that the traffic does not loop whether locally or somewhere else in the network. Again, this is the usual topology. So B is supposed to send traffic to PE2, and then suddenly the red link failed. If B sends the packet to C, if C is a little bit slow, C would tell it, yeah, why are you sending this to me? It should come back to you. Now maybe C was also fast, so it sends it to E. E will tell C the same thing, send the packet to me. So we don't want to do this. Okay, we want to make sure that we force the packet over the green path. And once it reaches E, we know that E is going to send the packet without any risk all the way to PE2. So we know that the shortest path from E to PE2 is via this path. So in reality, I need to force the packet one hop, and then a second, and then all the way to here. Again, we are going to use post-convergence path, again, for the same argument that we discussed for TI-LFA. And avoiding microloop avoidance should not really cause, or the idea is that should not really cause the packet to go somewhere else. So a link came up, and I'm supposed to use this link, I should be using it. Just because there is a guy that may be slow somewhere here, I will force the packet on the wrong place. So here's what we do. We have two stages. When a node converging for a destination does not trust the loop freeness, and again, this is something that either can be enabled by default, or the operator or the user can actually configure that on per node basis, per link basis, or per destination basis. It will actually, what it will do is that it will install an explicit path that would steer the packet until a point where it is sure that if the packet is left to flow freely, it will actually flow without risking any loops. After a short while, few hundred milliseconds, few seconds, totally up to the operator and the implementation, we'll just use the normal path, which means this is my new next hop. I'll just go ahead and send the packet to it instead of explicitly forcing it over this next hop, next hop, and so on. So again, complete coverage is guaranteed. For link down, I would say everybody expects that, be very similar to TI-LFA. Symmetric topology, maximum 2 is guaranteed, often 1 is enough. And if you think about it, your coverage for microloop avoidance would be actually usually higher than your coverage for TI-LFA, because the closer the failure to me, the more prefixes are impacted. So if the failure actually is far away from me, it is likely that less prefixes that come through me will get impacted. So if you have good coverage for TI-LFA, you probably have very good coverage for microloop avoidance. For asymmetric topology, again, it is most cases you get by with 2, but there will be few cases where you actually need more than 2. For link up, we can prove that it is 2, always 2. Doesn't matter whether it is symmetric, asymmetric, I don't care. It is 2. And if you think about it, it makes some sense. But this is provable.
So what is 2?
If the link, if any link in the network came up, I can guarantee loop freeness with at most 2 segments pushed on the packet. Again, no need for, it's incrementally deployable. In our example, let's say a link fails, I think it was link AD, and B is the rerouting node. So in this particular topology, I would probably need to send the packet to E, and then from E it will flow freely. Pretty much that's it. Any questions?
So can you go back?
Stuart.
Sorry, Stuart Bryan. Yeah. Could you go back? Hang on. Yes. Upon a topology change, when a node R, presumably that's for all nodes R, because all nodes who are now putting packets into the network need to be careful that their route is not going to be affected.
No. So again, Stefano is my downstream, and he's not supporting remote microloop avoidance. I do. If I impose the correct label stack,
yes,
that makes sure that there's no loops, Stefano doesn't need to do anything. If you think about it, it's actually easy.
I think we need to think about that, because I remember looking at many of these techniques over the years, and it was the point of entry that had to guarantee the loop freeness, because you couldn't guarantee the packet was ever going to go through the node that's doing the protection.
You're on right slide. So, but it says that a SAR pass is computed when event occurs.
Say that again? I didn't hear you.
You've got statements that you compute post-conversion pass after event has occurred.
Yes.
Which would involve control plane, so it defeats the purpose of fast reroute.
This is not really fast reroute. The objective is that I'm going to calculate a new path. If I let go the packet over the new path, the next hop may not have converged yet. It will bounce it back to me, or it will bounce it back to its previous next hop. Since I'm not sure which one of them is going to converge, I am capable of steering the packet or forcing it over the post-convergence, whether these guys are fast or not. So I will do it.
I understand why you're doing this, but it looks like you give a choice between fast reroute, where path is pre-calculated and pre-downloaded, versus loop-free or micro-loop converged path, which is slower.
Okay, so what you're saying is that during the period where I'm still in stage 1, I do not have protection. The answer is actually no. Because let's say I steer the packet again by sending it to Jeff and then Jeff to Stefano. I can still protect my path from you to you via another link. So even though I may be steering Jeff and Stefano to the destination, I will still protect the link that's directly next hop towards you via TI-LFA, because you're a normal prefix.
So fast reroute will kick in. You would use post-converged path you'll calculate one which is microloop free. You'll change your label stack.
Yeah, okay. I will force a label stack. Again, there will be two label stack. So first top stack is Jeff, and then the second stack is Stefan, and then the third label is the destination. Okay. Now, during that stage, which is a couple of seconds, some implementation will say, I won't be protected for 10 seconds. Some implementation, no, I want to be protected for each and every microsecond that I'm down. Fine, I'll protect the link from me to you, and then you protect the link from you to Stefan.
So perhaps it would be useful to go to your diagram to make the distinction between, say, B here, and which is the reconverging node, and A, which is the PLR.
Yeah. Okay. Maybe we were a little bit lazy in diagram. We should have circled this and used. Maybe should have put here RN to indicate that it's and put it in red. You're right. You're right. In this case, the rerouting node is B. In the case of TILFA, the PLR is A. So B, remember that if traffic arrives to B and destined to F, it should not be going to A in the first place because the red link is dead. I should be sending it to C, but if C is slow, it will bounce it back to me. So I'll make sure that the packet goes to E, and then from E, I know that E is a safe node. It will not bounce the packet to me. So I will let the packet free over there. Am I making sense?
So microloop happens immediately after the failure. If you wait to compute microloop free path and then instantiate it, you're already in microloop.
Right. So you actually so A is doing TILFA. So there are no loops. Okay. And then B converged. So it will no longer send traffic to A. It will send it to C. But C is slow, cheap. So we'll bounce it back to B. We don't want this. So I have protected myself using TILFA, but because C is slow, I end up losing more traffic. So what's the point of TILFA in this case? Instead of losing it right now, I'm going to lose it a second later. That's the point.
So once again, after A sees D goes down, it will start sending traffic over post-converge path without using adjacency seeds for microloop free, right? Because it needs to compute, control plane needs to compute and download back to LFIP and FIP entries, right?
So we do something called local repair. It's a different story. So when this link fails, it will wait for a few seconds and will continue to use the TILFA backup path, which we call local delay.
Which is exactly when microloop is going to happen within this.
Right. So because I'm using my TILFA path, I know that the path will not loop, but this is not the post-convergence path. So let me give an example. So A has calculated the post-convergence path this way. Okay? If when this link fails, A will continue to use the TILFA path. So traffic will flow over the post-convergence path nicely. Now suppose traffic arrives at B. So B says, oh, I am fast, I have reconverged. I will send it to C. Okay? But C is slow, so it will bounce it back to me. So you really need to have both TILFA and microloop avoidance. For traffic that arrives to A will use TILFA. For traffic that arrives to B, B will use microloop avoidance. Am I making sense? Any question?
So in TILFA, you mentioned you're considering SRLG as well. What about microloop avoidance?
True. Yes, we do convert. We do take care of SRLG today for local ones.
For microloop avoidance as well.
For microloop avoidances, of course, because okay. So
because
no, because SRLG is something that's attached to me. Okay, if something attaches to me fail, I have TILFA, which takes care of SRLG. Okay, for remote SRLG, we don't take care of it because it needs to be signaled and it can be anywhere, and it's a tough problem, really. Maybe we'll do it.
Can you go back to the picture of the network? That's it. There. Yeah. Right. So for the avoidance of doubt, right? I think this is a really nice trivial topology.
Right.
Now put 26 routers between A and E.
Between B and E?
Between B and E.
So if links are symmetric, it is guaranteed.
No. The point is that each and every one of those is going to have to converge in order for you to be microloop safe.
No.
Yes.
Once B converges and it imposes the correct label stack, I don't care what happens after B.
So is this only in a segment rooted environment? You're not talking about classic environment?
What do you say? What do you mean by classic environment? So C and E, there could be 26 routers. None of them know about TI-LFA.
Look, let's put a large number of routers between B and E.
Okay.
Yes?
Yes.
Packets could be entering in any one of those routers in a true topology.
Yes. Yes.
If they're, for half of them, they would originally prefer to get to your target via A. Every one of them needs to turn round before it is safe for them to continue to launch their packets in the normal, in the new direction.
Of course, if I want to protect something and the traffic arrives to that something, it needs to be able to protect it. If that thing can't protect it,
so the point is that it's not just one node that needs to engage in this process. All of the nodes that have to turn their path around need to engage in the loop prevention process.
No, because if you're talking about this, then
no. I'm talking about the ones.
No. I'll respond. Let's say A is TI-LFA aware, D is not. If A is TI-LFA aware, did I protect traffic or not? Do I have to have D knowing about TI-LFA in order for A to do TI-LFA?
But the microloops could occur anywhere in the
I agree. So as the point here, what you're saying is that in order to have network-wide protection, I need all nodes to react. The answer is yes, of course.
So are you helping Stuart's problem, Rtgwg, just by assuming that, well, okay, all the routers in the chain are doing segment routing? Is that the answer?
So a couple of small things. This is the name of this draft is microloop avoidance via segment routing. If you want to do something else, it's a different story, which is really not what I'm doing now.
So
we can do it.
I'm still worried about the routers in my long chain. This is too simple. I'm worried about my routers in my big ring that I've got here in the back.
Yeah.
Yes. So when the event gets noticed in the IGP, any one of them could notice first, and it could change its mind about which direction to send the packet.
Okay.
Yes?
So that's basics of shortest path.
Yes, that's absolutely the basis of
right.
shortest path.
If you are my downstream router,
yes,
after my calculation, I know if I send that packet, you're not going to send it back to me. Okay. So catches that you may be slow. So I need to make sure that I tell you where to send the packet after that. Okay. I am not sure why are you saying that C needs to be microloop aware in order for B to avoid microloops.
Well, well, let's have another router, a couple of routers in that.
No, let's say a C. Why do you need C to be microloop aware?
Oh, because if the packet arrives, well, C is on the horizon, so C will be fine. When C changes, C can change first. In fact, you have to have C change first in some of the methods.
If the traffic enters the network at C, what you're saying is yes.
C is fine, but now let's have some more routers between B and C and understand.
Okay, let's say I have a router here. I'm still missing what you're saying, but I'll go with you.
We are about to cut the discussion. We are 12 minutes over. Please take it to the list.
Yeah. Okay.
I think you need to read the loop prevention RFCs to.
Actually, I know this stuff. I have proofs for it, so I read it.
So AC Linux as described, I'd like to ask that Stuart summarize his topology for the minutes.
Because I did not get it at all. C is not routing the packet. C is looking at the label, the signal routing label.
Yeah.
That's the key, right?
Yes.
All right.
So B has told C what to do. Even whether C understands microloop avoidance or not, it's irrelevant. Now, traffic that arrives to C and destined to E, yes, C needs to do microloop avoidance.
It would be useful to clarify whether or not C needs to delay its fib update for the new shortest path.
No.
Okay, it would be good to clarify that though, because
the answer is no.
C
Stuart, we are done for this one.
C is on the event horizon. C does not need to do this. The really interesting case is if there are a significant number of routers between B and C, and you need to deal with that case. This is too trivial to understand the full problem.
Stuart, please send your questions to the list. Ahmed, would be good if you could address them.
Okay.
Gaurav? Thank you. Yes, kind of. Come on. Yeah.
Hello everyone, myself Gaurav Agrawal. So I will be introducing the MRT for segment routing today.
You probably want to move the microphone a little bit closer.
Okay. Can you please help me?
Can you advance it?
Okay. Okay, so a quick overview of MRT at the beginning. So as we all know, MRT is an FRR technology. It is capable of providing 100% coverage for node and link failures for IP and LDP traffic. And it's already a proven technology. We have the reference implementations available in the industry as of today for the MRT. And as we all know, the MRT architecture and both the framework is an IETF standard now. So what we are proposing is to reuse the same work what has been done for MRT for the segment routing. So the goal is to extend MRT for the segment routing. So now what is required to extend MRT for segment routing? The first thing what we need is the advertisement of the SR MRT capability. So for that, we need IGP extensions for the MRTs to be updated to carry that SR MRT capability. The second thing, what we need is specific for MRT option 1A, which is there as a part of MRT framework RFC. So for that, the SR needs to allocate 3 different labels corresponding to the 3 different MTID per segment. After that, these labels needs to be carried in IGP. So IGP extensions for SR as of today is capable enough to do that. So we don't need to do anything extra in that regard over there. And after that, the MRT algorithm can update and calculate the MRT forwarding topology. So before I move ahead, actually we have received some of the review suggestions regarding this approach. One of the review suggestion is rather than using MTID, we can use algorithm. So we feel for the SR, it's a very good suggestion. So that is something which we are going to incorporate in our coming draft.
Just let me know when you want to go. Just let me know when you want me to change the slide.
Okay, thank you. Okay. So for the MRT option 1B, basically we will reuse the topology ID label to identify the MRT forwarding topology and then use MRT algorithm to update the MRT forwarding topology. So for the option 1B, there will be nothing extra which will be required to support segment routing. Please. So basically MRT for segment routing will work both for the SRBE scenario, also for the SRTE scenario. So with this example, I will just try to explain how it will work for the SRBE with option 1A. So each and every node will advertise 3 labels, the default red and blue. And we can see here at the ingress, the destination 1006 label, which is a node label for the egress, will be added by the ingress. And in case if there is any failure between 1002 and 1004, the 1006 label will be swapped by 6006 label, which is to route the traffic to egress via red path. So this is the example of the SRBE scenario using option 1A, please. Similarly, for option 1B, the topology ID label red will be added by 1002. So basically, a red label will be added over the top of 1006, which will identify like the traffic has to be forwarded along the red path till the egress. So that is the only change in option 1B. Can I have a next slide? Okay. So similar lines, the MRT can work for the SRTE scenario also. So in this example, basically the ingress has added specifically like the explicit path where it is saying it wanted to go through 1004, then to 1005 to 1006. So if there is any failure between 1002 to 1004, basically the outer label 6004, which is 1004, which was there for this node, will be replaced by 6004, and traffic will be forwarded to 1004, from where it will carry out the normal forwarding path. So this is how it will work for SRBE scenarios also, SRTE scenarios also. Can I have a next slide? Okay. So just to summarize, basically the MRT work is already available. We see like with very minimal changes, the same work can be utilized for the segment routing FRR also. And that is what we are trying to propose here. The draft is in preliminary stages. We would like to get the community feedback and comments for the same. Thank you.
I've got one question. I'll stay here. So here, when failure occurs, you'll push label for yellow, or I'm colorblind, for another tree, right? So while second label, 1005, still represents another tree, it's meaningless on the secondary path. You would need to replace whole stack, not only the top label.
Actually, what we are saying here is like for the outer label, basically, the FRR will work. So basically, we at 1002, if the failure happens, it is the FRR will happen for the 1004 label, based on which it will be routed till 1004. So from here, basically 6004 will be replaced and the normal forwarding will be carried out.
So next label on the stack is 1005, which
Yes.
is on another tree.
Yes. Okay.
So you would need to get to another tree, doing practically turn around and going to the destination.
Okay.
So I think this is correct in that 1000, since you're basically doing a fast reroute to the far end of the failed link, then that 1005 is exactly the right label that the node on the other side of the failed link understands. So it's the label that it distributed by distributing the sRGB and the node SID for this algorithm, or that's the shortest path node SID.
Thank you.
Thank you.
What's next? Sam?
Not working. Just a second.
Hi there. This afternoon, my caffeine has worn out, so I'll read the slides. Just follow me. So today I'm going to talk about the gRPC. How many of you use gRPC? So whether directly or indirectly, if you use Google services, pretty much you're actually using gRPC. So we have published a couple of drafts, and I'm not the co-author on either of the drafts, but unfortunately the authors couldn't make it for this IETF, so I'm just representing them. So primarily, this presentation talks about the use case for the protocols details. You can actually go through the draft, and if you have further questions, you can always Google search, or you can, take it to the mailing list, and we should be able to answer there. Next slide, please.
To add, there's significant amount of information on grpc.io.
So what is gRPC? gRPC is Google's RPC service. So if you go back to history, it evolved from the way Google has built the services. And internally, it used to be called as Stubby. And over the time, it was refined, and it was published as an open source software, so anyone actually could contribute and use it as well. And so this is the fundamental infrastructure which drives pretty much all of the Google services. So what you see through any of, or what you get through any of the services, be it Google Cloud or any of the services, it actually is using the gRPC, and the same API what you get as a user is being used internally as well. So why we have to do this? So we just want to bring it to the community so community could benefit. And it is built over HTTP, HTTP2, and it is very, very compact in nature. So because we use binary framing and we use header compression, so it is very, very nimble, simple, and very usable. The fundamental nature of this is it's a bidirectional streaming. It supports bidirectional streaming, so that means you could actually stream the data. So you don't have to just rely on just the pull model, right? So traditionally, when you use in the network management or config and those kind of things, you are pretty much sending a request and you're waiting for the response or so on and so forth. But with lots and lots of data, streaming is the ideal or pretty much required kind of a requirement, right? So that's one of the things which drives the whole of the large-scale data. So streaming is very important. So this gRPC supports bidirectional streaming, and so that means it's not just one entity which is driving the data. So you can have multiple entities driving the data. The other aspect is you can actually multiplex the data and the stream. So that's one other aspect. So that means you could have offload the source of the streaming from the centralized route processor to line cards and so on and so forth. So you could distribute the streaming as well. So what are the features of gRPC, right? So one of the important aspect is it supports load balancing. So that means when you set up the streaming service as a server, so you could actually provide a source where you can actually access the streams or load balance paths, and even from the client side you can establish the similar mechanism to use load balance paths. So it's pretty much integrated into transport as well. So because it's a streaming data, so we use serialized, and we have a format called protobuf, which is very useful, very simple structure. So if you actually go and read through the actual details, it is pretty straightforward. You have the request, you have the response, and everything is structured in a protobuf format, which is very simple to define. And more importantly, the libraries and the language support, it supports right now up to 10 languages like C++, Go, Python, and all other languages. So it's multi-language supports, and it's open source. So anyone can contribute and be part of the open source movement. Next slide, please. So some of the use cases, right? So when you talk about the networks, we have fundamentally two aspects. One is config, and the other aspect is the actual management through telemetry data. So if you talk about the telemetry data, like monitoring the stats to the flow data and so on and so forth, you pretty much need to rely on the streaming. There are multiple ways you could actually monitor the data, but if you go to a full model, right? So you really have to wait for the actual data, the response to arrive, and then only you could parse the data and do that. But with streaming, you don't have to wait for the completion. So you could send the incremental data, and at the source, you could actually short the task so that you could stream the data in parts. But at the request side, or the one who is originating the request or subscribe to that particular stream of source, you could get the continuous data, and everything is pretty transparent. The infrastructure actually supports streaming. Question, Dan?
Yeah, Dan Bogdanovic. So when you're saying gRPCs, are you using protobufers or are you referring to flood buffers?
No, not protobuf is a structured format
Yes.
to specify how you can actually.
Yes, but are you using protobufs or using flood buffers? Because I know that
there is no. It's the gRPC supports multiple formats. It's not restricted to protobuf.
also I can choose it according to.
You could actually, if you go through the draft, you can actually find the details. So the other aspect is you could use this as a configuration option as well. This protocol supports configuration. So in fact, we actually have the running code. In fact, we are using it from forever kind of thing. So this supports both config as well as monitoring of the data. Next slide, please. So a simple architecture, right? So if you see the traditional model, right? When you want to monitor a specific network entity, you would access that entity through different methods, right? So if you go back 15, 20 years, we were using SNMP as a fundamental protocol to really access, and the data structures are defined using MIBs. So you send out a request, you wait for the response, and the way you do that is pretty much is driven by the client, right? So the server side will just wait for the request to arrive, and you do that. But you have to get away from that model, because the amount of data which you are doing that, you're trying to send it across is tremendous. So that means you cannot rely on that kind of model. So the streaming option, in this case, for example, you just need to subscribe to an entity saying that stream the data. And the data, the structure, you can actually define through the models which we have actually come up with, the open config models. So where you say that this is the structure of the data and you just stream the data. So all you have to do is specify that and you will get the stream of the data. So the protocol actually supports in a very, very seamless fashion. Next slide, please. So if you see what exactly we are doing for the streaming of the data, so we are compressing the data, and the whole of the data is in the binary format, so we are able to do that. So what will happen is when you are sending the amount of data, which is in a large scale environment, in previous talks, we actually told how actually we can monitor the data centers, where the amount of traffic is tremendous, because you need to monitor all the way from devices to the entities within the device, all the way to the network parameters. And if you really have to do that, we really need to transfer large-scale data. And we cannot achieve that with the existing model. So streaming, in this case, we need to support that. And on top of that, we need to ensure that it is actually compact enough that we don't overload the network. So, and on top of that, we have to have the bidirectional support. So it's not just always the unidirectional format. So that's one of the other criteria what gRPC brings to the table is that it supports bidirectional streaming. So in case of the data encodings, it is not restricted to one specific format. You could use XML, you could use JSON, you could use protobuf, so whatnot. So you can actually do that. And in the case of, as I was mentioning, for the language support, it does support multiple languages. Question, please?
Hi, Rick Taylor. I understand why you're underlining the fact that you've got efficient bulk transfer. My question really is, why are you concentrating on compressing the metadata around carrying the data out of carrying the data rather than just reducing the amount of data you're generating? So trying to do some intelligence with the data as close to the device that's generating.
You could do both.
Okay. It just seems odd to be concentrating on compressing the metadata around your bulk transfer rather than reducing the bulk in the first place.
You could do that, but if you really want more data, right, you're not limited by how exactly you want to send that or what exactly the data you want to send. So on the wire, you would definitely like to reduce as much as possible.
Hi, Oli Debut from Nuke. Just had a question regarding the use case itself. It seems to me like the use case. Walid Debut from Nuke. So it seems like the use case itself has been there for a long time. Like you could pretty much have like a network manager sitting on top of the box that would capture the data using SNMP and start streaming to your OSSs on top of the network manager. So subscription itself is already there for a long time. The streaming and subscription concept. To me, it comes down, the use case comes down to performance and scale. If I'm going to go with gRPC, have you guys you have any numbers on performance and scale, what gRPC can achieve?
I don't have the numbers at hand, but that's something you could always get
Sure.
you.
The second thing is, so the context, how would you put that in context with netconf notifications?
With respect to streaming or with respect
the streaming itself, the streaming gRPC streaming? How would that fit in place with the netconf notification concept?
So netconf has full-fledged streaming support. Is that what you mean, or
I know there's an RFC. I think 5277. I'm not really an expert in it, but I know it talks about netconf being able to stream notifications, something like that. So if anybody has more experience about it.
Sorry, Rob Shakir. One thing that's different between netconf notifications and some of the gRPC streaming is in netconf you need to explicitly define each notification that you want to be sent, right? So in Yang you tell me this is a notification and here's the contents of it. In the approach you're saying here the subscription can be to any arbitrary path. So you can receive essentially a notification against any data element that's defined anywhere in the Yang tree, which kind of simplifies. It means that you don't have to go explicitly through and figure out what it happened. And they might have different use cases, right? So for an event, you might not have a leaf that's associated with it. In the open config models, we've been careful to make sure we have leaves that you could subscribe to.
Hannes Gredler, I find the proposal to make this use for configurations highly interesting, and I would like to see actually some proposed models similarly to the open config model for Yang, right? So if you have actually a schema that you would like to see for things like, you know, configuring a set of BGP peers or something that is really more operational, I would be highly interested in that.
Okay. Okay. Point.
Lucia. Here. Yeah, is this the gRPC just for the point-to-point streaming or can do the point-to-multipoint stream?
You could subscribe to any from any source, right? So you could have multiple clients subscribe to the source. So you should be able to, but the streaming as such is point to point. So if you are asking if it is multicast,
yeah, I'm asking that the client server model, so the server can push down to multiple clients.
Yeah, so it's not like inbuilt multicast support, no.
Mehmet Ersin Nokia, at the same time NetConf co-chair. It will be my pleasure to challenge you a little bit. I would like to understand why you don't mention RESTconf in your draft at all. You mention netconf, you give that XML is the bad example, etc., but you don't mention anything about RESTconf and the use of JSON in case of RESTconf. I mean, the draft does not mention anything about RESTconf and the notification streams which are used with RESTconf, which is indeed a bit different to netconf. So we would like to see a comparison between the existing IETF technology and your version.
Sure.
There is the other question, interesting to me at least. What is your plan with this draft? It is stated to be informational. Is the far goal to standardize the Google technology?
So it's an open source project, and the reason why we brought to IETF is first point is to make sure that community is aware of it, and second aspect is we as the operator and few other operators who are actually using it in the networks, and the third of all, whether it is a standard or not, whether we want to drive towards standard is something we would like to see what the community feels. And at this point, we haven't made a decision
if you are
to go forward.
interested in the feedback of the community, please come over to Ops area where the network management people are, and they will be able to comment on configuration management, streaming, etc.
Absolutely. I did had a chat with Benova about this, and we agreed that we could discuss at large in the
If I may add, so the draft 00 version has been finished 2 hours before cut-off. People are extremely busy, and I'm grateful for what we've got. So I assume there's going to be more information. And why it's here, besides Google, it has to be implemented by remote end. So every networking vendor at some point, if they want to be with Google, they'll implement it. So it's really good to have common understanding of protocol structures, procedures, and what it is.
Alia Atlas. So first, thank you very much for bringing this here. I think it's really nice to see a large and fairly commonly used open source technology coming in for standardization. That's excellent. I am happy to talk about it here this time. And obviously last time we had discussion about telemetry and some of the streaming pieces, which is an area that I think there's a fair amount of interest in, and various proprietary implementations, as I believe your drafts talk about. We should probably talk offline and with Benoit. I've been chatting with others about what the right way forward is. Obviously, we have, I mean, the IETF does have a fully capable protocol in terms of for the configuration side with transactions and so on in netconf. And so I see there's a lot of promise on the streaming telemetry one. I think one of the concerns is being clear on the necessity or complexity level for configuration. RESTconf does handle some of the straightforward type of REST API providing. Another thing that would be useful to clarify is what type of models do you see this using? Obviously, Yang can compile down to XML, right? So clearly it can carry Yang models around. But is that what you're picturing? Are you picturing, is this this is how we can get push Yang telemetry out? Or are you picturing other things in terms of modeling?
So Yang is not the only thing we are looking for. Yang is one of the things because that is where all of the, at least the network side of things within IETF and other areas as well, where we are publishing the models. So this will benefit as a transport layer or transport mechanism. With respect to non-Yang stuff, we actually in fact use it beyond the Yang. And for all of our infrastructure we monitor is beyond that. So.
Rtgwg again. Specifically for the Yang OpenConfig case, there's a reference protobuf that shows how, which you can then use to build a gRPC endpoint. And I actually have some open source gRPC implementations that show how that can be used. So the intention at the moment there is it's encoded as JSON and carried in a payload of a specific proto.
Jeff House, is there any desire to also bring protobufs in for standardization?
Is it in the draft? No. So that means I don't know the answer. So I can get back to you.
Outside of the draft. No. So I'll offer one comment if that's the case. Protobufs is a relatively simplistic language at the moment.
Yeah.
It's lacking some of the richness that we have in other things like CBOR, ASN1, and also Yang. So if that's even if that's not a desire, maybe there should be some consideration to expanding the typing.
I will take the feedback to the
There
audience.
are a few more slides to go. Maybe we keep questions till Sam has finished.
Okay, next slide. So on similar lines for the configuration, it supports pretty much what we need in terms of configuration, and these requirements we have beaten to death in different areas. So I don't have to belabor on that. Next slide, please. So what is the status of gRPC as such, right? Not just the stubby. So gRPC, we actually, after open sourcing, so now we have multiple vendors supporting in terms of telemetry, as well as config as well. So as you can see, we have a few vendors who already support the telemetry data streaming through support on the platforms. And also in terms of configuration, we do have few vendors, and if you go through the actual use case draft, it has different links where it points to different notifications in the press and other stuff. Next slide. So additional use cases, some of the things which were just briefly mentioned but not in detail, or like multi-language communications, which is very key as well. The important thing is the existing iOS and Android has support for gRPC, and so that means all the way from mobile platforms to the high-end network gear, you have the complete set of support with gRPC. And as I was mentioning, it is very efficient because we were able to use it, and I could vouch for it as an implementer of the gRPC clients. I know how usable it is. And so all of the stuff, if you're using any of the cloud services, the data you actually could stream in and out is on gRPC aware platform. So that means you get what you see in the services as open source platform as well. Next slide. I think that's pretty much it. So you can go through some of the additional data points, but that sums it up gRPC from use case perspective. If you go to grpc.io, you can actually find further information about the source and the Git details, so you can actually download and play around with it. Any questions?
2 minutes for questions.
Thank you very much.
Sam, thank you for taking it, and thank you for bringing it to IETF.
So go ahead and come on up, Jen. And I'm going to give a little bit of background while we set up this. We had a virtual interim about a month and a half ago to focus on provider-signed multi-homing, and that was a good experience, I think. After that, we realized there was a need, we think, for a document that takes kind of a holistic view of the problem and doesn't try to segment it into just the routing aspects or just the host aspects. As you can see from this document, well, if you've taken a look at the document or the presentation, there's really two big aspects, the routing, and then that's sort of the easy part. The difficult part is actually how hosts can choose the right source address for packets to go out to the right ISP in this scenario. And actually, I've asked Jen to focus actually more on the host aspects, because I think that in the routing area, we tend to not understand or not pay that much attention to the host aspects. And there are a lot of requirements that come out of the fact that the host actually need to do something very difficult, which is choose a source address based on a failed uplink, for example. So I'll let you jump off. Oh, one other aspect though is we, at this point, see this document as really living in both Rtgwg and v6 ops. It could potentially also have some implications for 6-man as well. But instead of splitting it into multiple documents, we want it to be a single document so that we can simply get the work done and then adjust the process accordingly.
Yeah, so, okay, great, yeah. So I spent some time trying to deploy IPv6 in various networks, and we still have one big problem. If we have an enterprise network which do not run BGP, and those networks use provider address space, you cannot properly do multi-homing. You can do some dirty hacks for more than one uplink, trying to send packets to the right uplink, assuming providers doing BCP38, but everything gets very nasty when uplinks goes down or some disruptions happening in the network, right? So first problem is how can I send packet to the right ISP, because ISP might implement BCP38 or the uplink might implement BCP38. The second problem, how I implement policies, like I want to use one ISP for internet, I want to use second ISP as a backup, or I want to use both of them, or second ISP is just for particular services and so on. And again, how do we react to failure scenarios? Next slide, please. Yeah, and we don't want to use network address translations. We all hate it, right? We all know it's bad, and it's been some work done explaining why, right? So we're trying to find a solution without using network address translations. So first part of the problem is how to send packet to the right ISP. Obviously, we need to look at source address. There is no other way, right? We need to know that this ISP accepts only packets from the address space, so we need to route based on source as well. And this is the first part of the draft called source address dependent routing. But the most interesting part, at least from my perspective, is how can we react to the various failure scenarios, what to do, and how can we influence the host decision, how can host select the right source address. Because it's v6 world, and unlike IPv4, hosts normally have multiple addresses, right? So in v4 you can assume host has just one address, and in v6 it's okay to have more than one, but in some cases you cannot use particular address because uplink went down, it's just not, doesn't comply with the policy. So next slide, please. So we can assume particular expectations here, some assumptions being made that the enterprise network has 2 or probably more uplinks. And again, as I said, we only should send packets from which have source addresses from particular address block to ISP, which gave that block to a company. So we could not send just random uplink. And if we cannot send packets because, for example, uplink went down and there is nowhere to send the packet, such error scenario should be signaled to the host. And it might be some use case when particular ISP provides some services, and those services should be reachable only from address space from that ISP, and we need to cover this as well. And indeed, everything should work as before. I mean, intra-site communication shouldn't be affected. So introducing multi-homing in IPv6 on PA address space should not make user experience in that network worse. So next slide, please. Okay, so we tried to cover various scenarios, so we kind of came up with some topology to explain what we're trying to do. So in this case, we have some site edge routers which connect to ISPs. And as you can see on this slide, we assume that, for example, ISP-B can have some services like host 61, which should be reachable only from red address blocks, while, for example, you might send internet traffic through ISPA by default using blue address space from ISPA. So indeed, in real life, it might be much simpler topologies in many cases, like just one router connected to two ISP or two routers connected to two ISPs, but we are trying to make the solution reasonably generic. So next slide. So, okay, let's look at the simplest part of the solution, just network, how network can send packet to a correct uplink. So basically, the solution is quite simple. Instead of having one forwarding table, we creating scoped forwarding tables. So for each uplink, for each source address block, we created the forwarding tables scoped to that particular source. And you might or might not actually have unscoped forwarding table, or in other words, forwarding table which is scoped to all addresses. And the beauty of this solution is that you can actually deploy it incrementally. You can do incremental rollout when in the first step, only site edge routers connected to ISPs need to have those scoped forwarding tables. All other routers in the network could just send packets based on the destination as long as that packet reaches the site edge router. Site edge router will look at scoped forwarding table and select a proper destination. Indeed, in the generic scenarios, when those site edge routers are not directly connected to each other, you might need to find a way to deliver traffic from first site edge router to the right one, right? And in this case, you might need, for example, tunneling, and indeed it might means that packet might take some suboptimal path. Question?
Yes, Julius Probacek. When you say that you can work with just edge routers supporting SADR, are you supposing that they're all neighbors of each other?
No, it's what I say. Can you show the topology, example topology slide? So yeah, actually, can you go forward because I have a slide showing next. Yeah. So here basically, it's a scenario when only side edge routers have a scoped forwarding table, all these blue and pink squares. In this case, let's say host 31 send a packet using the red address block, and it reaches the first side edge router by using just destination routing, and then side edge router needs somehow, and we do not cover it, it's right now in the draft, send it to the correct one based on the scope forwarding table. It might be tunnel.
Okay.
It might be tunnel, or you might create some kind of links between them, or you might start rolling out, if your topology complex enough, you might start rolling out SADR to the rest of the network.
So in effect, at layer 3, they are neighbors, since they have tunnels.
It's much simpler if they are neighbors on layer 3. If they are not, you need to somehow make them neighbors by tunneling, for example. We do not cover it currently. I'm actually not sure if it should be in scope of this draft. Might be, we might add more details later. It's already 44 pages. Nobody has read it.
Okay, thank you very much. That answers my question.
To the very end, I mean, some people managed to get to the middle of the draft. So, wow. So, yeah, back to, so basically we created those scoped forwarding tables. There are 3 steps. I put some text from the draft on the slide, but you don't have to read it because I have a picture on the next slide, I think.
Next slide.
Yeah, so basically first 2 steps, routers, let's say all those routers on the left side advertise some prefixes. You see, for example, side H router A and B, they already support SADR, so they advertise scoped and unscoped prefixes, like blue prefixes scoped to ISP A block, red prefixes scoped ISP block, and some other routers which are just standard legacy, not SADR capable routers, just advertised basically unscoped destination. And then our router R8, which is supposedly capable of doing source address dependent routing, creates 3 forwarding tables. One is scoped for blue addresses, so only blue routes going into the table. Another table scoped to red prefixes, and there is an unscoped forwarding table which we normally have on other routers. So next slide. And there is a third step when we basically combine unscoped and scoped forwarding tables to make sure that if some routes, some destinations present only in unscoped forwarding table, we add them to scoped. So for example, as you can see on the slide, route to one particular /64 exists only in unscoped forwarding table. It does not exist in any of scoped, so we added there. So packets from red or blue source could still reach the destination. This is more specific instead of following the default. It basically to avoiding the situation when packets will forward using default routes instead of more specifics from unscoped table. Next slide, please. Yeah, and forwarding again, quite simple. A router should look at the source, find the proper scoped forwarding table, then look at the scoped forwarding table for the source. If there is no scoped forwarding table matching that source, then unscoped forwarding table will be used. Next slide. Yeah, it's interesting. One unexpected side effect is, let's say all your routers support unscoped forwarding, support SADR. So potentially you can get rid of unscoped forwarding table, which means only source, so only packets from legitimate source could be forwarded. We kind of getting BCP38 out of the box. You could not anymore leak packets with some link local, site local, ULA source, which I'm still seeing in the internet.
Pedro on the Telefonica, since you have this light on the projector right now, when I read this, I wondered why you were continuously duplicating all the tables. Don't you think that having this unscoped routes in all tables may be somehow inefficient when the routing table actually grows? I mean, I could see this unscoped forwarding table being the whole routing table for the internet, IPv6, which I expect will grow. And then if I have to replicate it another 3 times for the scoped routes, I don't know if I like it.
So I think it's a kind of interesting implementation details. We might actually have a policy specifying what we're actually replicating. Yeah, it's a good point. Yeah, so potentially, yeah, you're not necessarily going to have full view on your enterprise routers, but yeah, we might think about, yeah, what exactly should be copied there.
Well, so to be clear, this is the routing table inside of the enterprise. And so it, could be default routes plus the other routes that you want to differentiate in terms of which ISP you go to. So for this scale of enterprise that is using PA multi-homing, I think there's a reasonable argument for this not being the whole internet routing table. However, if that's a common use case, then we need to figure out how to deal with it.
So basically, I believe if you're receiving full view, it means you're most likely running BGP, and if you're running BGP, it's probably not a your use case. You're probably using your own address space. But we are talking about situation when it's a corporate network small enough, not running BGP. That's the key thing, right? So it has to use PA, provider, address space provided by ISP.
So question, Robert Hannes Redler, previous comment, full FIP today is 80 megabytes, right? That shouldn't bring down a host to its knees, right?
Robert? Yeah, so Robert Rashuk. So at last IETF, Davey presented an idea to do source destination-based routing, both in RIB and FIB. How do you compare your solution with multiple tables to source destination lookup?
Are you talking about source destination draft?
Yeah, from
Sure.
yeah.
So, I mean, there's an existing draft in the routing area working group, which was originally proposed in the context of this problem for HomeNet, and it's basically the same problem. It could be that these two are actually different views of the same solution. However, we sort of started from the requirements for enterprise multi-homing and said, okay, what do we need to do? And we have yet to reconcile the two views of source address routing. They may actually be just different versions of the same thing, or different, and could be implemented, in the same or different ways, different implementation versions. We need to figure that out. But we sort of started out with the requirements driving, how to look at these, and at least looking at the routing tables in this scoped manner seems intuitively easy for operators to understand. And so we may come back to that, and we need to figure out how the two are reconciled.
Jeff, perhaps I've missed it, or it's later in the presentation. Do you discuss how we get the different classes of prefixes into the red versus blue versus the non-scoped?
No, we don't discuss it in the draft. I do not. So far, it's quite abstract. Like we somehow magically create two scope forwarding tables, right? How exactly? I believe it's going to depend on your routing protocol and how you communicate with the ISP, right? Because it might be the DHCP prefix delegation even, right? It might be static configuration. My ISP gave me /48, do whatever you want with it, and it statically routes the /48 to me. So I have probably statically configured edge routers, and then using my IGP or BGP or whatever I use in the corporate network to populate those forwarding tables. I believe it's going to be protocol dependent.
I will take most of my comment to list, but the BGP comment made me think that one of the common cases for even regular V4 is that you may be a dual home stub. The only thing that may differ in this particular case is that you may have different addresses from each stub, and you're using the BGP data to help classify things into one of these red versus blue. I'm happy to talk about that with you later.
Yeah, so in terms of how the source scoped destination routes get propagated through the enterprise, that's fairly straightforward in at least a link state protocol, and I think in distance vector one can come up with a similar version. The idea of how those are fed in to the IGP, the simplest way to think of it is they're static routes. However, that could also be, but it will always be injected, I believe, at the site edge routers. And so either static routes or BGP injecting those is a fairly reasonable way to do it. But we keep it abstract at the moment, but yes.
Per, 2 comments. First, well, let's do it a stack like +1 to the BGP scenario. I think it's going to be very common. And then another thing, I remember a person who said that there would only be a market for 4 computers in the world. And I remember another person who said, so 32 bits, we have more addresses than we are ever going to be using. And look where we are right now. So all these things about, well, now it's only 80 megabytes. I take it with a lot of care, and sometimes even with fear.
Rtgwg, I think we should attempt to move on from this discussion, because how you represent the routing tables is an implementation detail. I suspect that actually there's the semantics. There's two different types of semantics, and you can implement it like this, or you can implement it with one source specific routing table, and it's going to be the same semantics. So, this is really only a representation for our convenience, in the sense that the source address indexes into a square which is colored. Okay, but how it's implemented in the FIB is completely different, and it can be done differently, and we should not get hung up on this. How a square becomes colored is depending on where the route came from. So if you have a BGP feed from level 3 and a BGP feed from someone else, then you tag those feeds and that's it, or if they're static routes and so on. So I think that the actual hard part of this stuff comes later, so
yeah.
We actually have 40 minutes, so I think we're we're good for this, but thanks.
Okay, Julius Probacek, he's absolutely right. So one way to look at it is that the routing tables that you've seen in the draft that you were mentioning earlier, which I believe is Trone and Baker, map quite cleanly to multiple routing tables of this kind. So it requires some work, but it can be done incrementally. It can handle something that Jen is glossing over, that is the possibility of having overlapping, non-disjoint source prefixes. And that's stuff that has been shown by Boutier and published in IETF Networking 2015.
Okay, so let's move on because, yeah, I consider this being quite straightforward. Yeah, so next slide. Yeah, so it's, as I said, it's an incremental rollout. Let's do it on H first, and then we can slowly upgrade our routers over time. So next slide. Yeah, and in this case, yeah, as long as all routers in the network support SADR, it becomes simpler because packets will probably take shortest paths and so on. So next slide. Okay, great. Host, next slide. So how can we tell host what to do? Because when everything works, it's simple, right? I can actually do it with policy-based routing currently, which is ugly, but I can do that. But what if I want host to use particular source because either uplink went down or I want to use it blue ISP to access internet because it's cheaper, for example. So there is a source address selection algorithm on a host. I specify an RFC, and if you look at all those rules, there are a few rules which are actually applicable, might be interesting in our case. One rule, rule 3, is try not to use deprecated address. So if I make address deprecated, host will try not to use it if there are non-deprecated address. Great. Another interesting rule is rule 5.5, which says that if...
You know, maybe in the context of this room, explaining what deprecated is would be good, because when I first read it, I thought it was something else.
Okay, sorry, yeah. Assumptions. So, life cycle of IPv6 address. When host configures IPv6 address, for example, after receiving a router advertisement from a router and using stateless address router configuration, the address will be valid for a while until preferred lifetime timer expires. So every time a host receives new array for that prefix, it will again restart preferred lifetime. If there is no updates for that prefix coming, then after a while the address will be preferred lifetime timer expires and address will become deprecated. It will be still valid, but it will be deprecated, which means it could be used for accepting incoming packets to that address. For example, if we already have some connection, some type of existing communication to that host, but it will not be used by default unless there are non-deprecated addresses available for initiating new connections. And then after valid lifetime timer expire, it will become invalid. It will not be used at all. So how we control it? In router advertisement for a particular prefix, there is a timer saying, here is your preferred lifetime, like 7 days, for example. So you can use addresses from that prefix for 7 days. After 7 days, they're becoming deprecated. So don't use them for new connections, but only accept packets. And after like 30 days, I think by default, it will become invalid. If I send an array with preferred lifetime 0, it will immediately tell host, okay, the address is deprecated, don't try to use it if you have any other addresses. Okay, so rule 5.5, back to rule 5.5. If I have two next hops advertising, one next hop, one router advertises one prefix in array, and another next hop advertises another prefix in array, host will indeed configure addresses from both prefixes. Exactly our multi-homing scenario. And rule 5.5 says that if during the next hop selection, host decides to use next hop router A for sending traffic, it should use the addresses from prefix which was advertised by that next hop. So basically I have two routers, one router sends me blue prefix, another router sends me red prefix, host has two addresses, red and blue, and now it wants to send internet traffic to a hop to router A. It means the source address will be blue. because router A sends only prefix information option for auto configuration from blue address space. Okay, let's remember this for a while. So next slide, please. How we actually can configure any address on a host? There is a DHCPv6 option, and there is a stateless auto configuration. So in case of DHCPv6, we can basically influence another rule which was on the previous slide. If two addresses have same label, then if your destination and your source has the same label in the special label table, then use that particular source. And for using stateless auto configuration, as I say, we can influence the source address by influencing next hop selection. And indeed, we can deprecate an address, which means that address not going to be used. And I'll discuss the mechanism later. And indeed, if none of those options work, network should be still able to send an ICMP back to host saying, okay, sorry, could not forward your packet anywhere, wrong source address. Next slide, please. So we looked at DHCPv6. The draft has more details about it, but the takeaway is, yes, we can potentially specify a custom label table and say, okay, for services in blue network or in red network, please use only red addresses. And there is even RFC describing how you can send such a custom label table to host using DHCPv6. It could be actually stateless DHCPv6. You don't have to use DHCPv6 stateful for address assignment. However, next slide, please. It looks quite complicated. First of all, not all hosts support DHCPv6, so you could not rely on host to understand it. Secondly, I am not sure the RFC for which describes how to send this policy table from DHCP server to a host is actually widely deployed. And third thing is, as a network administrator, I'm a bit confused. So now I have to manually configure on those red addresses in the policy table, and I'm pretty sure people will make mistakes, and it actually does not scale very well. And another issue is the scalability. So if my uplinks went down, now I have to reconfigure all hosts in the network, telling them, yeah, don't use these labels anymore. And the DHCP server actually might be somewhere far away. It might be in the data center, right? I might have a small office which got this policy table via DHCPv6, and then uplink went down, and how can we communicate to my DHCP server and data center and try to reconfigure all hosts in the network at the same time? Because if it's not in the same time, it means it will be significant delay in case of network failure. Lorenzo, you have comments?
Does this even work at all? Because it can assign labels to addresses, right? But can it tell you that like that if you're trying to connect to something outside the network, can it even tell you what the right thing is to do is? It can't tell you where to send the packet, right?
Yes. So basically, the idea is there is a default policy table, right? And in the default policy table for all destinations, all your addresses, red and blue, will have the same label. Now, what I'm trying to do, let's for red destinations use red source by using this policy, but it's really hard because my DHCP server now needs to know about all topology changes. My uplinks going up and down, I have to send it somehow to a host, DHCP server, and it's not host at all to know about topology change. Routers do know, hosts don't. So
no, but I'm wondering if it works at all. Like, how do you color like the prefixes from ISP-A?
Yeah, so apparently it looks like it needs to be manually configured or somehow, so that's why I don't like this solution.
And if you have two defaults, how do you color them?
So, exactly, so draft has more details about why it does not work. We just looked into this, came to conclusions, no, it's not recommended, strongly not recommended. Well, so next slide, please. Let's forget about DHCPv6 in this scenario. Okay, example topology, just to remind you, what we trying to cover two ISPs. Some traffic should be sent through ISPB because it's ISPB specific services, like I don't know, video service or something. And for internet, for example, we might try to use blue ISP. So next slide. Okay, how it works now before any like multi-homing or source address dependent routing. So let's say router number 3 has two prefixes and sends both prefixes in router advertisement. I'd say, okay, I'm your default router, so router lifetime is higher than 0, and it sends two prefix information options, blue and red, which could be used by a host for stateless router configuration. And it also can actually send some route information options saying, hey, by the way, you can reach those particular more specific routes through me. Not all operating system understands that, but it's possible. So now we need to solve problem of telling host, so this source should be used for those destinations, and red source should be used for another destinations. Potentially, in long term, we can come up with some new array option and say, here is your routing table, right? Use those source and destination pairs and get all that policy we were talking about to a host from a router and update it when some network topology change happens. However, it does require new array option, which means changing all those hosts we have in the wild. And it's going to take a while, and I don't want to wait. I have this problem, I've been having this problem for a while, and I want to solve it now. So can we somehow at least do not touch most of the hosts, so at least some of them? Because to be honest, I'm operating the network. It's much simpler for me to upgrade some routers than upgrade all those operating systems, especially in bring your own device model when I don't even know what I'm having in the network. So I have an idea. Next slide, please. So we just discussed rule 5.5. If instead of one router, I have two routers, and each router advertises only one prefix, either blue or red, it's simple, right? A host will use one router, it will automatically pick up the right source address. So let's pretend that instead of having one router in the network, which supports source address destination routing, I have two virtual routers. So let my router 3, pretend to be two different routers. One router connected to ISP-A, another router is connected to ISP-B. So let one physical router, which has two scoped forwarding table, send two different arrays. It will generate two different link local addresses and send two arrays, one or more arrays, one per scoped forwarding table. If I have 3 ISPs, okay, it's going to be 3 different arrays. 3 different link local source. It could actually say, because there is RFC which specifies default router preference. So let's say I want to send internet traffic through blue ISP. In this case, blue array will have a router lifetime, which means I'm a default router, and set router preference high. And red array will have router preference low, which automatically means, okay, now I have a preferred default router out of 2, 3, or whatever. And because each router advertises one particular prefix for auto configuration, host will automatically pick up the right source address. If on top of this, I want the host to use red addresses to reach some particular destinations in red ISP, I can advertise route information option in red array and say, okay, I am your default router with preference low. And by the way, you still can reach some particular destinations through the red next hop. And it means, again, now internet traffic going through blue link with blue source addresses, and those particular /64 in red ISP-B network will be reachable from source addresses from the red prefix. It kind of solves most of use cases we were thinking about. And again, it looks like not a protocol change on a router, it's kind of feature. And I say there is a dirty hack which I can do right now. It's basically connecting each ISP to VRF. Yeah, it's nasty, so I want it to be clean. So next slide, please. It's all looks very well when we have all uplinks up, everything is working. But if I am going to assume that all uplinks are up, I actually don't need multi-homing. I can live with one ISP. So now, let's say red uplink to internet, not to the particular services in red network, went down. So what's happened? Most likely, red scoped forwarding table does not have default route anymore. And if forwarding table doesn't have default route, it does make sense that this router should not be your default router. So R3 immediately advertised array with router lifetime 0, which indicates to a host, I'm not your default router. It could still advertise router information option. I'm not your default router, but you can reach some destinations, some particular more specifics, sending packets to me. In this case, we're still able, if it's, again, possible from topology point of view, send packets from red source to particular /64. I think it's a kind of case, yeah, when you have particular link only to services in ISPB and not to the internet. Okay, next slide. Let's say all connectivity to ISPB went down. Now hosts should not be using red source addresses at all. So it means actually that most likely forwarding table scoped to red address space will be empty. In this case, there is no way to send packets from red source anywhere, which means red prefixes should not be used. In this case, router can immediately send array and deprecate red source address on the host by setting preferred lifetime 0 for a red prefix. Again, host automatically deprecate the address. It will be using only blue address for any communications. Now, next slide, please. Oh, even more interesting corner case. What if all uplinks went down? Okay, now the router doesn't have anything in scope forwarding tables. It could not send any packets anywhere. The problem is, if it's not just a very, very small network when we have 1 or 2 routers and all hosts connected to it, but it's more complex network infrastructure on site, I might still want to allow host-to-host local communications. I want to talk to printers or my workstation and so on. Great, how can we solve this? There are different options, and I think one of the ways to solve it is on the next slide. Let's use ULAs. Let's generate a ULA for a site, create another scoped table for ULA, do not advertise any defaults, because you should not be sending packets from ULA source anywhere outside of a site. In this case, the whole ULA prefix just advertised in router information option in RIO. So host knows that this yellow next hop can be used to reach any ULA source, but should not be used for any internet destinations. In this case, even if, next slide please, even if both uplinks went down, a host could still talk to each other on site. And actually one side benefit is, from my perspective, if network needs to change ISP, you don't need to renumber your infrastructure. If you use ULAs for your infrastructure and only for infrastructure, only for internal communication, it's quite simple, right? You can still have all connectivity intra-site. It doesn't matter if uplinks are up or down. Next slide. Yeah, and indeed, we still need to be able to signal errors. All the mechanism which has been described would probably allow to cover most of the cases, but if host still sending packet which we cannot forward, there is a already existing ICMP error message saying source address error. We actually do not know how hosts reacting currently to such message. Maybe trying to pick up another one, maybe not. It might be again implementation dependent. The problem, we cannot rely on this mechanism alone. That's why we were discussing how can we make sure host selecting the right source address in most of the cases, because if I'm just relying on ICMP, it means if topology changes and all my hosts still using the wrong address, most likely ICMP will be rate limited on a router. There are software limits, there are hardware limits on the line card and so on. So ICMP alone could not be reliable enough. So, but we indeed still need to have a mechanism to signal errors back to host. Next slide, please. Yeah, so summary. So first part of the solution, network. We need source address dependent routing. So packets will be routed based on a combination of source and destination. Good news is, in the minimal requirement is to deploy it on the edge. But ideally, as I explained, if your first hop router supports it, it makes life much, much easier. Probably it's, the way to go is to deploy it on the edge, deploy it on the first hop routers. You can actually leave core, if you have core, untouched, either for a while or forever. Next slide, please. Yeah, on the host. So using rule 5.5 allows to influence source address selection on a host by influencing the next hop selection. If hosts support rule 5.5, unfortunately, RFC says that not all implementations track actually map next hop and prefixes advertised. So some implementations might just do not keep any tracking, so they do not know which prefix was advertised by which next hop. But if hosts support rule 5.5, which is a standard RFC, and if hosts support RFC 4191, which is for default router preference and more specific route option, then we do not need to require any changes on the host. So it will currently work out of the box if your first hop router support SIDR and would be able to send scoped, I call them scoped array specifics to scoped forwarding table. And again, if topology is complex enough, so local connectivity is required, even in case of all uplinks failure, it is recommended to use ULA. Oh yeah, Lawrence, I know you don't like ULAs.
Rtgwg, actually, no. So I'm wondering if for stuff that doesn't support 4191 and Rule 5.5, if you have ULAs, that fixes the problem in a different way, right?
No, because I need ULA only to enable host-to-host communication on site. I do need Rule 5.5. Could you go back to slide when I'm showing these two arrays being sent? Can you remember the number? Oh yeah, for example, this one, right? If my host do not select router based on, it doesn't support default router preference, I cannot say, please use blue ISP for internet because my red one is backup.
But all you need to do is make all the arrays come from the same link local address and it will work. Just send the arrays from the same link local address, FE80::1, include all the prefixes, including the ULA, it works. You send it to that router does SADR, it works. If one uplink goes down, you deprecate that source prefix and it works. If another uplink goes down, you deprecate
it would not, that. Okay, I want to cover a case when, for example, my red uplink to internet went down, but I still able to access some of the local services in ISPB. I need RIO for this, right? I still want to say, use blue one for internet access, use red one for those particular destinations, particular.
Yeah, but that requires host changes to a lot of hosts. I'm thinking there's something that you can deploy without that.
Okay, actually, some scenarios, some multi-homing scenarios can be covered with minimal changes, right? We're trying to be a little bit more generic and cover something better than just two routers connected to two ISP, because yes, it's simple.
Okay. So we'll cut the line after Julius and take these two questions, and then I think that was your last slide anyway, so we'll wrap it up.
Yeah. Was that described in the draft? Because I think that's a much more deployable solution than your more rich one.
Okay, let's get it offline, because at 0.0 draft, we still need to polish text indeed, yeah, so.
I'm not trying to make this quick. Data Linux doesn't implement 5.5 as a rule. It also doesn't implement the ISMP policy mismatch thing, it just ignores that. Yeah, I agree on that. It can't be implemented, was Lawrence's comment. Also, if you go with the Lawrence's approach of sending all of the arrays from the same link local, you fix the broken case, but you don't support the working case. So I think the multiple link locals is actually the best idea I've seen so far for making the host select the best source address in a center scenario. And whoever came up with this, I'm really thankful for this. So, yay.
So hi, Julius Krobacek. I have one question and one comment. So the question is, so I guess it's a statement. I'm extremely confused because you're the person who explained to me why RIOs wouldn't work for that. And what I understood was that when you are routing through a given router that is announcing a route over a RIO, you cannot guarantee that the host is using the right source address. So I've probably missed something.
So again,
I have two routers that are advertising different destinations. Using RIOs, as you suggest, does not guarantee that they pick the right source address, does it? So what's the mechanism that makes sure that the source address is...
so okay, host first need to select a next hop, based either because it's its default router, or it's because some more specific prefix was sent in RIO, right?
Yes.
Then after next hop has been selected, address from the prefix advertised by the next hop in prefix information option will be selected. If I basically have, yeah, it's 5.5.
Okay, so it's something that I don't, okay. Okay, the rule 5.5 in the, okay.
Yeah.
Okay. Okay, that answered my question, thank you.
Yeah.
And the other thing is, we definitely need network layer mechanism for that. So that's very good work, and it's great to have network layer mechanism. I'd just like to point out that a different approach for dealing, or perhaps a complementary approach for dealing with source-specific routing, is to have solutions at the transport and application layers that will either pick all source addresses at the same time, think an online game that is sending the data from all source addresses and whichever arrives first wins, or by probing the different source addresses.
Probing will introduce significant delay.
I know. I'd just like to say that there is a IETF standards track protocol that does that, and that has been found out to work beautifully well with source-specific routing. We almost cried when we first tried it out, and that is MPTCP, which appears to have been created for source-specific routing. Thank you.
Thank you, everybody. We are 10 minutes over time, and I'll see you tomorrow.
Hold on. Yeah, I think that well. Good job.